Welcome to Analytical Chemistry Vision, a platform dedicated to exploring the theoretical and experimental aspects of chemistry, blending classroom learning with laboratory research to enhance understanding and inspire innovation in chemical science. Let us begin a highly interesting and useful topic for UG, PG, and research students: microwave or rotational spectroscopy. Microwave spectroscopy is important in real sample analysis for identifying gas phase molecules, pollutants, and atmospheric species. It enables structural characterization, isotopic analysis, and detection of trace components. In microwave or rotational spectroscopy, we will learn following topics. First one is principle of microwave spectroscopy. Second one is general features of rotating system. Third one is classification of rigid rotators based on moment of inertia. Fourth one is expression for energy of rigid rotator diatomic molecule. Fifth one is intensity of rotational spectral lines. Sixth one is isotopic substitution on rotational spectra. Seventh one is expression for energy of non-rigid rotator diatomic molecule. Eighth one is instrumentation and applications of microwave spectroscopy. Ninth is numerical problems. 10th is questions on microwave spectroscopy. Here, questions arises: why we learn microwave, rotational spectroscopy? And the reason is to determine molecular structure and bond lengths accurately, to calculate moments of inertia of molecule, to understand gas phase molecular motion and energy quantization, to identify the molecules in interstellar space, astrochemistry, to detect atmospheric gases and pollutants, to study of isotopic composition of molecules. Let us see, what is microwave spectroscopy? Microwave spectroscopy is a technique in which microwave radiation interacts with molecules, resulting in rotational transitions that provide information about molecular structure and geometry. This spectroscopy is also called as the rotational spectroscopy. Here, we will consider the simple example of linear rigid rotator diatomic molecule to understand the microwave spectroscopy. A linear rigid rotator diatomic molecule is an idealized model in which two atoms, M1 and M2, are treated as point masses connected by a fixed bond length, are rotating about their center of mass, as shown in the image here. Here we will learn the conditions for microwave spectroscopy. First condition is, a molecule has a rotational spectrum only if it has a permanent dipole moment. Most heteronuclear molecules possess a permanent dipole moment. Example, HCl, NO, CO, H2. Second one is, molecules can interact with electromagnetic radiation, absorbing or emitting a photon of frequency, nu, if they possess an electric dipole moment, oscillating at the same frequency. Next, importance of dipole moment requirement for microwave spectroscopy. This figure shows the periodic change in permanent dipole moment as a polar molecule rotates with time. The oscillating dipole interacts with microwave radiation, producing absorption. Homonuclear diatomic molecules, O2, H2, Cl2, lack a permanent dipole moment and therefore do not exhibit microwave spectra. Here, we will know the general features of rotating systems. Linear velocity, v, is defined as distance traveled per unit time. In rotational motion, angular velocity, omega, represents the angle swept in radians per unit time. Here, the diagram showing a mass m rotating at a distance r from the center has linear velocity tangential to the path. The moment of inertia of rotating molecule, I, is equal to m, r, square, measures resistance to changes in rotational motion and is the rotational analog of mass. Next, the moment of inertia of a polyatomic molecule depends on the masses of all atoms, m1, m2 and m3, and their distances, r, from the rotation axis, determining its rotational energy levels and microwave spectra. This diagram explains the physical meaning of moment of inertia. Here, m.1, m2, and m3 represents the mass of the rotating body, while r, I, is the perpendicular distance of each mass element from the axis of rotation. The moment of inertia is given by I is equal to summation of m, I into square of r, I, showing that mass farther from the axis contributes more strongly to resistance against changes in rotational motion. Let us understand the classification of rigid rotators based on moment of inertia. A molecule can have three principal moments of inertia, Ia, Ib, and Ic, corresponding to three mutually perpendicular axes of rotation. Ia is moment of inertia along the bond axis, Ib is moment of inertia when molecule rotate on plane of paper, and Ic is moment of inertia when molecule rotates on perpendicular to the plane of paper. The relative magnitudes of these moments determine the type of rigid rotor. First, classification is linear diatomic rotator. Examples are HCl, carbonyl sulfide, acetylene, carbon dioxide. Consider the HCl molecule shown in the image, where Ia, Ib, and Ic are respective moment of inertia in their axes. For linear molecule, Ia equal to 0 and Ib equal to Ic. The moment of inertia Ia equal to 0 because rotation along the bond axis has no mass displacement. Ib equal to Ic because the mass distribution about both axes is identical, so the moments of inertia are equal. Next, second classification is symmetric tops rotors. Examples: ammonia, methyl cyanide, fluoromethane. Let us take example of methyl fluoride molecule shown here in image, which is prolate symmetric top molecule. Molecule rotation about the principal symmetry axis gives a smaller moment of inertia, Ia, while rotation about the two perpendicular axes gives equal moments of inertia, Ib, equal to Ic. Thus, Ia less than Ib equal to Ic. Take another example of BH3, an oblate symmetric top molecule with a planar trigonal structure. Rotation perpendicular to the molecular plane has a larger moment of inertia, Ia, whereas rotation within the plane gives equal moments of inertia, Ib, equal to Ic. Hence, Ia greater than Ib, equal to Ic. This slide illustrates spherical top rotors, where molecules such as methane, silicon tetrafluoride, and silicon hexafluoride possess highly symmetric three-dimensional structures. Due to uniform mass distribution about the center of mass, rotation about the bond axis, Ia, in the molecular plane, Ib, or perpendicular to the plane, Ic, encounters identical resistance. Hence, all three principal moments of inertia are equal, Ia, equal to Ib, equal to Ic. These molecules lack a permanent dipole moment and therefore do not exhibit pure rotational microwave spectra. Fourth one is asymmetric tops rotors, and examples are water, methanol, vinyl chloride and formaldehyde. This slide explains asymmetric top rotors, where the molecular mass is unevenly distributed about the three principal axes. As a result, the moments of inertia about the bond axis, in plane axis, and perpendicular axis are all different. That is, Ia is not equal to Ib, and not equal to Ic. Because these molecules possess a permanent dipole moment, they exhibit rich and complex rotational spectra in microwave spectroscopy. Here, we will see the derivation of the energy expression for a rigid rotator diatomic molecule. Two atoms with masses m1 and m2 are separated by a fixed bond length, r0. But their respective distances from center of gravity c is r1 and r2. At the center of gravity, m1 r1 equals to m2 r2, which is equation 1. Further, from this equation, m1 equals to m2 r2 divided by r1. And similarly, m2 equals to m1 r1 divided by r2. Thus, moment of inertia of diatomic molecule is given by I equals m1 r1 square plus m2 r2 square, which is equation 2. We know the moment of inertia for diatomic molecule, Ib equals Ic and Ia is 0. Putting the values in equation 2 and solving it becomes. Finally, I equals to r1, r2 into m1 plus m2, which can written as equation 3. Further, at the center of gravity, as we know that m1 r1 equals m2 r2, and since r1 plus r2 is r0, r2 will equal to r0 minus r1. Substituting the value of r2 in above equation, r1 finally equal to m2 r0 divided by m1 plus m2, and r2 equal to m1 r0 divided by m1 plus m2. And further putting values of r1 and r2 in equation 3, and solving, I equals to m1 m2 divided by m1 plus m2. Or it can also written as, I equal to mu into square of r0, where mu is reduced mass. The unit of moment of inertia is kilogram-meter squared. This slide shows the rotational energy expression for a rigid rotator diatomic molecule. From the solution of the Schrödinger equation, the rotational energy of a rigid rotator in joules is given by Ej equals h squared divided by 8 phi square I into j plus 1, where j is the rotational quantum number with values 0, 1, 2, and so on. I is moment of inertia equals mu into square of r. Mu is reduced mass, r is internuclear distance. Further, to express the rotational energy, joule in wave numbers, we use the relations. As we know that Ej equals to h into nu, and nu bar equals 1 by lambda, wavelength, and putting these values. Epsilon j, in wave number will be equals to Ej divided by hc, and further solving, finally the energy expression for rigid rotator diatomic molecule in wave number will be, epsilon j will be h divided by 8 phi square Ic into j plus 1. Further, it can be written as epsilon equals bj into j plus 1, where b is rotational constant equals to h divided by 8 phi square Ic. A selection rule defines the condition that determines which transitions between quantized energy levels are allowed and which are forbidden during the interaction of radiation with molecules. For a rigid diatomic rotator, the rotational selection rule is del J equals to plus minus 1. A transition with del J equals plus minus 1 corresponds to absorption of radiation, where the molecule moves from a lower rotational level to a higher one. On the right side of the slide, the allowed rotational energy levels are shown for quantum numbers J equal 1, 2, 3, 4, 5, and 6, so on. The upward arrows indicate absorption transitions between adjacent rotational levels, while downward transitions represent emission. Thus, only transitions between neighboring rotational levels are allowed, which leads to a series of spaced spectral lines in the microwave region for rigid diatomic molecules. Here we can determine the allowed rotational energy levels of a rigid diatomic molecule using selection rule. As we know that epsilon j equals bj into j plus 1. Putting the values of j equals to 0, 1, 2, 3, so on. The calculated epsilon j values will be 0, 2b, 6b, 12b, and similarly, 20b, 30b and 42b values are obtained. Based on calculation of epsilon j values for different j, diagram for allowed rotational energy levels is prepared shown right hand side. Thus, the rotational energy increases with increasing j, and the spacing between successive levels also increases, which is a characteristic feature of a rigid rotator diatomic molecule. Next, here we will understand the allowed rotational transitions between energy levels of diatomic molecule and spectrum arising from them. For this, difference between two energy levels are calculated. For the transition J0 to J1, del epsilon j equals to epsilon j1 minus epsilon j0, which is 2b minus 0. And final difference value is 2b. Similarly, for transition J1 to J2 and J2 to J3 is calculated given here. The difference in energy levels are 4b and 6b. Based on the difference in energy levels for different transitions, spectrum can be drawn, given here. Thus, the separation between successive rotational spectral lines is 2b, which is a characteristic feature of the microwave spectrum of a rigid diatomic molecule. These allowed transitions give rise to the observed rotational spectrum. The intensity of spectral lines in microwave spectroscopy is governed by two main factors. First one is Boltzmann distribution, and second one is degeneracy in the energy states. Let us see Boltzmann distribution. It determines the population of molecules in different rotational energy levels at a given temperature. According to Boltzmann statistics, lower energy levels are more populated than higher ones, so transitions originating from lower J levels generally show higher intensity. The equation of Boltzmann distribution law is Nj by N0 equals to e to the power minus Ej by kT, and further putting the value of Ej, which is energy of rigid rotator molecule, it becomes Nj divided N0 equals to e to the power minus Bj into J plus 1 and Hc divided by kT, where Nj is number of molecules present in the J levels and N0 is number of molecules present in the ground level, J equals to 0. B is rotational constant, K is Boltzmann constant and T is temperature. Here we can understand the effect of the rotational quantum number J on molecular population using the Boltzmann distribution. Let us consider hydrogen chloride, HCl, as an example. For HCl, the rotational constant B is taken as 10.6 per, the temperature is 300 Kelvin. The values of Planck's constant, Boltzmann, the speed of light, is given here. Putting the value in Boltzmann distribution equation. For J equals 0, the exponential term becomes 0, so N0 by N0 is 1. For J equals 1, the population ratio decreases to about 0.903. Similarly, for J equals 2, the population ratio decreases to about 0.737. The graph on the right clearly shows that as the rotational quantum number J increases, the population of molecules in higher energy levels decreases exponentially. This decrease in population directly affects the intensity of rotational spectral lines in microwave spectroscopy. This slide explains the effect of temperature on the Boltzmann distribution of rotational energy levels. Consider the B, J, H, C, K as constant. At a temperature of 300 Kelvin, the exponential term becomes e to the power minus 1 divided by 300, which is approximately 0.9966. Similarly, when the temperature is increased to 400 Kelvin, the term becomes e to the power minus 1 divided by 400, giving a higher value of about 0.9975. The graph on the right compares population distributions at 300 K and 400 Kelvin K at higher temperature. The population spreads over higher rotational quantum numbers, and the maximum shifts to larger values. Thus, increasing temperature increases the population of higher rotational levels and enhances the intensity of higher frequency microwave spectral lines. Here, we can understand that how the rotational constant, B, affects the Boltzmann distribution of rotational energy levels. From the Boltzmann distribution law, it is clear that the population depends directly on the value of the rotational constant B. For larger values of B, the energy spacing between rotational levels increases, causing the exponential term to decrease more rapidly. As an example, when B equal to 5 per centimeter and B equal to 10 per centimeter, the graph on the right compares population distributions for different values of B. It shows that molecules with larger rotational constants have fewer molecules in higher J levels. Therefore, an increase in the rotational constant reduces the population of higher rotational states and affects the intensity pattern of microwave rotational spectra. Degeneracy of energy states is another factor that affects the signal intensity of rotational spectroscopy. Degeneracy refers to the existence of more than two quantum states having the same energy. For a rotating molecule, the kinetic energy of rotation is given by E equal to 1 by 2 into I into omega square, where I is the moment of inertia and omega is an angular velocity. The angular momentum P is defined as P equals to I into omega. Substituting this into the kinetic energy expression, we obtain A equals to P square by 2I. We know the rotational energy of a rigid rotator is A equal to h square divided by 8 phi square I into jj plus 1. Finally, rearranging and solving all the steps, this equation gives P equals to h by 2 phi into square root of j into j plus 1. This result shows that for a given rotational quantum number J, multiple orientations of angular momentum are possible, leading to degeneracy of the rotational energy levels. Further, angular momentum and degeneracy of rotational energy levels for a rigid rotator. We know P equals to h by 2 phi into square root of j into j plus 1. Here, h and phi is constant. Thus, degeneracy of rotational energy levels, P depends on value of j. Putting the value of j equals to 1. P will be 1.14, which is equivalent to 1. P is quantized, so it takes a direction such that the value of P along the reference direction are -1, 0 and +1. In addition, number of degeneracy can be determined by using following formula: 2j, j plus 1, when j equal 1, the degeneracy will be 3. Thus, the molecule can rotate in 3 directions as shown in image. Similarly, when putting the value of j equals to 2, P becomes 2.44. which is equivalent to 2. P is quantized, so it takes a direction such that the value of P along the reference direction are -2, -1, 0, 1 and 2. Thus, the molecule can rotate in 5 directions as shown in image. and number of degeneracy will be 5. Based on this, there are 5 number of modes by which molecule rotates as shown in the image. Thus, degeneracy increases the population level and therefore contributes directly to the intensity of the corresponding rotational spectral lines. This slide explains how isotopic substitution affects the rotational spectra of diatomic molecules. The rotational constant B of a diatomic molecule is given by B equal to h by 8 phi square IC, where I equals mu r square is the moment of inertia, mu is the reduced mass, and r is the bond length. When one isotope is substituted, the bond length remains almost unchanged, but the reduced mass changes. As a result, the moment of inertia changes, leading to a change in the rotational constant. For two isotopic species, the ratio of rotational constants is given by equation 1, the ratio of B single prime by B double prime equals to I double prime by I single prime equals mu double prime by mu single prime. Here, symbols B single prime, B double prime, I single prime, I double prime, mu single prime, and mu double prime refer to rotational constants, moment of inertia, and reduced masses for 12 carbon and oxygen 16 and 13 carbon and oxygen 16, respectively. This diagram illustrates the effect of isotopic substitution on the rotational energy levels and rotational spectrum of a diatomic molecule, carbon monoxide, CO. On the left, the rotational energy levels of 12 carbon, 16 oxygen are shown for rotational quantum numbers J, from 0 to 5. On the right, the corresponding levels for 13 carbon, 16 oxygen are displayed. Although the electronic structure and bond length remain almost the same after isotopic substitution, the mass of the carbon atom increases, which increases the reduced mass, mu, of the molecule. Based on this, carbon-13 has a larger reduced mass, its moment of inertia is higher and its rotational constant is smaller. Thus, the rotational energy levels of carbon-13 are more closely spaced, and its rotational spectral lines appear at lower wave numbers compared to carbon-12, as shown in the spectrum at the bottom. In a real diatomic molecule, the bond is not perfectly rigid. As the molecule rotates faster, the centrifugal force stretches the bond length, shown in given image here. This effect is known as centrifugal distortion. The rotational constant B is given by B equals h by 8 phi square IC. Since the moment of inertia, I equal to mu r square, we see that B is inversely proportional to r square. Therefore, as the rotational quantum number J increases, the bond length r increases and the rotational constant B decreases. To account for this non-rigid behavior, the Schrödinger equation gives the rotational energy, Ej, in the form of Joule, equation number 1. The energy in Joule is converted to wave number by dividing with Hc. Equation number 2 shows the energy in wave number, which is further simplified to epsilon j equals to Bj into j plus 1 minus dj square into j plus 1 square per centimeter. Where d is called as distortion constant, the constant d depends on molecular parameters and is given here. Further, the selection rule for non-rigid rotator is del j equal to plus minus 1. Based on the possible allowed transition can be calculated as given here. On the left, the rigid rotor model is shown, where the bond length is assumed to be constant. The rotational energy levels are given by epsilon j equal to Bj into j plus 1, where j equal to 0, 1, 2, 3, so on. On the right, the non-rigid rotor model includes the effect of centrifugal distortion. As the rotational quantum number J increases, the molecule rotates faster, causing the bond length to increase slightly. This increases the moment of inertia and decreases the rotational constant. The energy levels are therefore modified to epsilon j equal to Bj into j plus 1 minus dj square, j plus 1 square. Where dis the centrifugal distortion constant. Because of this correction term, the spacing between adjacent energy levels becomes smaller at higher values. This effect is clearly seen in the spectrum at the bottom. Unlike the rigid rotor case, red lines, the non-rigid rotor lines, blue lines, shift progressively toward lower wave numbers and are no longer equally spaced. Next, we will see instrumentation of microwave spectroscopy. First one is radiation source. The klystron generates tunable microwave radiation of wavelength 1 to 30 cm required to induce rotational transitions in polar molecules. Second one is Waveguides. These are hollow, rectangular tubes, made of silver or copper-coated metal, which efficiently guide microwave radiation with minimal energy loss from the source to the detector. Third is sample and sample chamber. Sample is normally gas and sample is retained in a piece of evacuated waveguide by very thin mica window. Fourth is detector. Detector converts the transmitted microwave signal into an electrical signal. Commonly, a crystal detector or radio receiver is used. Here, we will see the applications of microwave spectroscopy. Microwave spectroscopy is applied to determine molecular structure, bond lengths, and dipole moments through rotational spectra. It is widely used for gas phase analysis, identification of atmospheric pollutants, detection of interstellar molecules, investigation of water vapor, and study of chemical kinetics, molecular interactions, and fundamental molecular constants. Further, more applications of microwave spectroscopy. Chemical kinetics. Understanding the kinetics of chemical reactions is essential in chemistry. Microwave spectroscopy can provide data on the rates of chemical reactions by monitoring changes in molecular rotation. Food industry. In the food industry, microwave spectroscopy can be employed for quality control and food safety. It helps in identifying contaminants and ensuring the purity of food products. Materials science. Researchers use microwave spectroscopy to study the properties of materials, including polymers and ceramics. It can provide insights into the molecular structure and behavior of these materials. Here, let us see the numerical problems that are commonly asked in microwave spectroscopy. Questions is: the first rotational line in the rotational spectrum of CO is observed at 3.84235 per centimeter. Calculate the rotational constant, B, and bond length of CO. The relative atomic weight carbon, oxygen and hydrogen is given here. There are 3 steps to calculate B. Reduced mass, mu in bond length, R, given here. Finally, the value of B is 1.92118. And bond length is 1.131 angstrom, given here. Here, another similar question for determination of rotational constant, B, reduced mass and bond length, R of HCl, which is calculated in 3 easy steps, shown here. Let us see, here some reasoning types questions from microwave spectroscopy. Can we solve? Here some more, short type questions. Here some long answer type questions. Here, more some long answer type questions. This video lecture is prepared by this given reference book. Please read this book for more details. Thank you for watching the Analytical Chemistry Vision. If you like this video, please visit our channel for more other interesting theoretical and experimental lectures. Don't forget to like, share, and subscribe, and share your feedback in the comments to help us improve further. Thank you.